Hi, my name is Bruno. I'm a PhD student at the Vilnius University, and today I'm going to talk about galactic habitability. So first, let's see what habitability really means. Well, it's actually the property of planet to host liquid water on its surface. So it's a ring around a star. If you are inner to this ring, you will find hotter temperatures and water will evaporate. If you find yourself farther, the water will be an ice and it will not be a liquid. So there is a just right spot for water to be. But over years, it's been known that water is just not sufficient. There are many more factors in play. For example, now I will show you. These are just one of the aspects of planetary habitability. So water is just the only one. It's important, but we need to include many more. Just like atmosphere, and we need to have magnetic field to hold it. The star needs to be stable for a longer time to life to evolve, and so on and so on. But now the question is, do we just keep looking at the star and the planets there, or we just maybe look outside of it and we find some greater area? For example, let's not focus on finding on each planet water, does it have tectonics, is it tidal locked, but let's expand it and let's see, is there a place in the galaxy where these conditions are found, where we can find those planets that are important for us. So the underlying concept of galactic habitability is that, okay, life is rare, but not because the ability to develop is hard, but probably because of the cosmic environment. And we will now explore our Milky Way galaxy because we live in it and we have explored it the most. So our Milky Way is one of the many spiral galaxies in the universe. It contains from 100 to 400 billion stars, and it's almost as old as the universe, about 13 billion years old. It's been structured into a halo, bulged in a thick disk and dark matter halo, and its diameter is around 100,000 light years. So let's go briefly through our galaxy, these substructures. First is the bulge. The bulge, it has a spherical shape. It's one of the oldest part of our galaxy and hosts many stars. It also hosts a supermassive black hole. Around these stars revolve, but in these chaotic orbits that are pressure supported. Next we have a disk. It is where the majority of star is born and it resides. It can be divided into thin disk, which are more younger stars, and the thick, where are older stars, and there is where our gas dust appears, and where the spiral arms are the locations of star formation. And it is characterized by these orderly and rotation supported motion. Next we find the stellar halo, which is like in spherical in shape, and it's also where many ancient or very old stars are found, also global clusters. But most of these stars are actually not from our galaxy, but they came from other, probably dwarf galaxies, which are now accreted, and we find them as stellar streams. It also is pressure supported. And the next, and the largest portion of Milky Way is the dark matter halo, so it's composed of dark matter, which is most of our galaxy by mass, and it actually touches the other galaxies, and we know about it when we take a look at how stars orbit. All right, now once we have a galaxy, now we will see what are the primary factors of the galactic habitability. So in this talk I will talk about how the ratios of elements help us determine where habitable planets can form, how proximity to stars can help us a bit to tell how life will evolve, and these energetic events in forms of supernovae and can be maybe detrimental for our lives. So let's start with metallicity. It's actually iron, one of the most abundant element in the universe, and it's called metallicity because astronomers have this habit of calling all elements beside hydrogen and helium metals, because they only them, well, a bit of lithium and beryllium, they were forged in the Big Bang. And we can see that it has been shown that the giant planets are found only around the metal-rich stars, whereas Earth-like planets can be found at around any metallicity. But what's the main problem? The more giant planets we have, the less Earth-like planets we have, because more material will go into these gas giants, and then less will be available for Earths, and because of the migration, probably Earth-like planets can be launched into their host stars. And it can be seen that for this metallicity or high metallicity, so on x-axis is the mass of the planet, and now we see that for very high metallicity, many giants but very less Earth-like, and as we go down, so the green and blue are lesser metallicities, we see that virtually no giant planets are there, but we have many Earth-like planets. And because of the stellar density and metallicity in our galaxy, most of the planets we found are in the bulge in our thin disk. And because there is this luminosity-metallicity relation, and since our Milky Way is one of the most luminous galaxies in the nearby universe, we expect that there are many galaxies that are yet to form these habitable worlds. Next, we go to the carbon to oxygen ratio, which tell us what kind of planets we are supposed to expect. So around 0.8 is the limit. Below that value, we expect more silicates and oxides on our planets, which means we expect Earth-like worlds, water worlds. If that ratio is higher, that means we will get these dry planets, but with some exotic minerals. For example, these diamond worlds. Looking at our solar neighborhood, we see that the ratio is now about 0.55, which means we are still making these rocky planets just like the Earth. But because of the galactic chemical evolution, the oxygen is mainly produced in supernovae type 2, which we'll be discussing later, but they are sign of early star formation, and carbon is from these late stars, from HB stars, which means we expect this ratio to get higher, and that means we expect drier planets in the future. Next are ratios of magnesium and iron over silicon. Magnesium over silicon will tell us what kind of mineralogy we are expecting. So if the ratio is roughly less than 1, we expect silicon-rich planets, more than 2 magnesium, and in between around Earth-like. This ratio will tell us more about mantle viscosity and about plate tectonics, which will make volcanoes active. Next, is the iron over silicon, which is actually telling us what's the ratio between the core and mantle. So the smaller the core, the larger the mantle, which means that plate tectonics can be successful. And as we can see, the silicon, which is produced in both supernovae 2 and 1a, but iron is mostly produced in supernovae 1a means that this ratio will be getting lower and lower, which means our planets will get larger and larger, will have larger cores, which means lower mantles, and unfortunately no plate tectonics into the future. Lastly, these are some radioactive elements: uranium, thorium, and potassium, which heat the surface of the interior of the Earth, which makes then plate tectonics happen more often, and that means we have more these cycles that are important, like a carbon cycle and sulfur cycle for us. And since these elements here are also diminishing into the future, it means that future planets will have less heat available from the formation, and then plate tectonics will not be efficient. Next, we go to these stellar encounters. So once the star passes close to the sun, it will perturb these outer skirts, which is made of many icy objects, so-called Oort cloud, and then it will inject comets to the inner solar system. If the flyby is even closer, it can destabilize the orbits of the planets, and that means it will increase, for example, eccentricity, and then the insolation, so how many energy is coming to the planet, will not be stable, and that means it will affect habitability. Also, these instabilities in the outer part can amplify instabilities in the inner part. And all of this is actually dependent on the mass of the star that is passing by, how close does it pass, and what's actually the configuration of the system. Next are so in a solar neighborhood, our closest star is Alpha Centauri, and we can see that in about 1 million years we will get around 10 stars that will come closer than 1 parsec, and only one encounter which will be closer than 0.1 parsec, but it is per 50 million years, and it will be Gliese 710. It's not visible me, sorry, but here it's supposed to be that planet, so it will be really, really close, and it will appear as the brightest star close to us. Also, authors of this paper speculated that these are the chances for the civilization to hop on other planets and slowly but surely explore and inhabit all of our galaxy. To compare, we see that in a bulge, the stellar encounters are even fiercer, so the stars can even get closer to the 0.05 parsecs, and even then the orbit of Neptune and Uranus or Saturn at 10 AU, 10 astronomical units. Getting to extremes, this in a globular cluster, this is example of Omega Centauri. We see that for every million years a star passes around 0.5 AU, so closer, almost as the orbit of Mercury. How that looks like, actually, this is some artist impression on the left, how the sky looks like if we are in a global cluster. So basically no light, it's always no darkness, always light. And on the right side we see that this is from the Earth, so we can see that not many stars. Last thing is these energetic events that come in a form of very high energy photons, so X-ray, gamma rays, and it could be protons of cosmic rays. How they operate? Well, they will destroy the ozone layer and leave our planet not unprotected. And the important thing is that it also depends on how long these events last. And we know about these events because there are some imprints of it in the lunar samples, buried in the deep snow and buried in the deep ocean. For example, isotope of iron, 60 iron, is only produced in supernovae, as well as plutonium-244. These energetic events are mostly supernovae, gamma ray bursts, and kilonovae, but because gamma ray bursts and kilonovae are so infrequent, we'll only be doing supernovae, which And then we go to the supernovae type 2, which are produced by these massive stars at the end of their lives. They are mostly found in the spider galaxy, and they contribute to early chemical enrichment, and they leave only neutron star or a black hole. On the other hand, supernovae type I1A, are binary stars composed of white dwarf, so the remnants of small mass stars, and they happen to be in all types of galaxies, and they're all, because they are old, they contribute to late chemical enrichment of the galaxy. But they are more energetic, and no remnant remains after the explosion. So what happens when the Earth and the Sun goes into spiral arm or the interstellar medium? The heliosphere, so this magnetic bubble that protects us, will shrink. Here how it looks like about the simulation about 2 million years ago. So the heliosphere is only about 0.2 astronomical units, so less than a Mercury orbit, which means all planets are there, are unprotected. And we can actually see that many of these events coincide with mass extinctions. Here is some examples. So in this we see on y-axis the rise of iron 60 around, so it will be 3, 4, 5 million years ago, which is connected to this Pliocene Pleistocene boundary. And after knowing all this, we can see how our galactic habitable zone looks like. Well, it's a ring around the galaxy around 8 kiloparsecs, where in the inner side of the disk there are many metal-rich stars, so they do not host habitable planets, and the supernovae are still high. But on the outskirts, we see that not that supernovae, but stars are metal poor, hence no planets yet. So we did galactic habitability, we talked about it, but this is only also a part of the story. As we can see, habitability is a complex thing. I only here listed some of these elements that are important, but there are of course many other, and probably many things that we still haven't discovered that are important yet. And after this, we can ask ourselves, are we living actually in the golden age of Milky Way? Well, so the time is a bit running out because these radiogenic elements are slowly drifting away. Metallicity is getting higher and higher, so more giant planets. But there is still a chance for us. And actually, it depends on our closest, one of the closest neighbors, which is Andromeda Galaxy. So we are supposed to collide with it in about 4 to 5 billion years, which will induce, when these gas collide, it will compress and start a new star formation. But actually, sorry, here it's not visible, but around 50% chance is whether we collide or not. And that actually depends on our second neighbor, which is Triangle Galaxy M33. So depending on the kinematics, when probably with Gaia DR4 or some better surveys, we will actually see and we will calculate whether we are going to collide. So to conclude this talk, we see that habitability is very complex. There are still many things unanswered. And for our Milky Way, it's about a ring around 80 kiloparsecs, but it's still fuzzy. It's not that strictly as can be planetary habitable zone, but it's slowly spreading because metallicity and because lower supernova rates. But our planets are getting higher cores, so no plate tectonics, and the interiors will not be as molten, of course, again, for plate tectonics. But next probable merger with Andromeda will help us. So once we merge, it will induce star formation and influx of new elements which can synthesize and make new planets.